One of the things that I liked in JEE was the packaging model. And I think one of the things that was figured out pretty well at the time was that an application is built out of different modules. And as part of the fact that it was built out of different modules, they created that type of hierarchy. And that hierarchy included the assembly root, the web modules that we all know as a WAR, an application client model, and some other modules, and also a description, a meta description that described those modules and how they relate to one another. Now, if you look at that definition, that kind of helped to define pretty well what a Java application looks like, what is it comprised of. And that model was actually very successful. I think one of the best things that came out of J2E was that definition. So in many ways, this is the type of, I think one of the first time that there was an attempt to define an application in a broader spectrum. And that's kind of, that was the interesting experience from that world. Now the thing that have changed that we need to take care of from that experience, it's not that that model is wrong or broken or anything of that line, just that the world have changed since the definition came out to the world. When the definition came to the world, one of the main assumptions is that the world is very much Java-centric. Everything is going to be in Java. That's how J2E was built. Everything is going to be Java. And therefore, our world is Java, and our definition of application is in Java, and everything is in Java. Obviously, the world is a little bit different today. It's more heterogeneous. And one of the assumptions was that everything that is non-Java is pretty much out of scope. So for example, even in a Java application, if we have a load balancer, if we have a database, it doesn't fit into that packaging world, right? So you wouldn't be able to put in a WAR file a definition of the actual database and how it is installed. Or the same thing for the load balancer. The other thing is that it doesn't really assume that the application changed quite a bit in terms of scale and size and all of those other things. A lot of the definition was fairly static. So a lot of the things that are dynamics are kind of outside of that meta definition. So for example, having meta definition for scaling doesn't exist in that definition. So that's another aspect that when we move to a cloud kind of world, we need to add to that type of definitions. We'll talk more about that later on. So if we really look at all of those things, and what are the things that have changed, as I mentioned earlier, the world is not Java-centric. We have a world in which we need to combine Java plus a lot of other languages, and it becomes more common today than it was in the past. Cloud in itself, as a data center, enforces us to think of automation as something that is pretty baked right into the development. And I think you had this talk of Gradle. How many people here was in this talk of Gradle? Okay, so you're pretty much familiar with that concept of continuous development. So a lot of the concept of cloud actually now become part of our development. It's not something that is done by operations in the data center, and we have to think about it early on. The other thing that we have is a lot of open source projects, tons of them, that we want to integrate with to speed up our development. And we don't want to think about integration as an embedding thing, right? We don't want to embed them into our application and change the WAR file or change the jar file or change meta configuration every time that we want to use a project. So we want to think about integration in a more broader spectrum as a service kind of model. And that's kind of, I would say, that the few items that have changed that needs to change the way we deploy application, and I'll talk more about that again in a second. So that's the other motivation that we have here. So if we really look at the same packaging model, trying to map it to that new world, it will look something like this. So we'll have an application, and below that application, we'll have a bunch of services. Services, unlike jar files, are not necessarily a package of libraries that sits in one file. There would be different files, potentially, that could live in different places, but will have one definition of how they relate to one another. Okay, it's the same thing that we have in web.xml or something like that, but the difference is that they don't necessarily need to be packaged in one file. So think about it in that way, and that will help you, and I'll show you what that means in a second. The other definition is that the package can be an application which is basically a bunch of processes interconnected to one another. And again, it's not Java-centric. Bear in mind that I mentioned processes, and a process could be mapped to Java, but it doesn't have to be Java. A process on an operating system could be anything. So once we work at a process level, we're pretty much agnostic on the language by which it was produced. And that's another thing that gives us the ability to define the application context, if you'd like, without binding it to a particular language. So we have an application. A pod is basically a way to say that we have services that needs to be interrelated to one another in an affinity model, meaning that they need to sit in the same machine, for example. So the services are decoupled from one another at some point, but in some cases we do want to say, you know, that web tier and that database tier needs to sit on the same machine because we don't really scale them separately. And in a lot of the assembly, especially in multi-tenant SaaS applications, you do build application like that. So for example, when Salesforce provision a machine, they provision the machine with a database with a lot of components in that machine that serves, let's say, 100 customers per machine. And that's how they provision their SaaS operation. It's very common in a SaaS world to build the entire environment like that. So you build stacks, combine them together, you know that they're going to serve that amount of load, and then you pile them out, and that becomes your application. So we need to have that construct as well as part of the definition. And as I mentioned, they're interrelated to one another, so there is some dependency. The difference in that dependency, as opposed to, let's say, the Spring definition of injection, or as opposed to the web XML definition of injection, the difference is that it's going to be distributed, meaning that it's not a container, a single container that's going to build all those libraries and wire them up. It's going to be a distributed deployment. So we're going to have a web talking to a database, and they're going to be interrelated, meaning that when we launch the database, we need to notify the web container that this is where the place in which that database exists. When we deploy the application, we don't know where the database exists. We don't even need to assume where it exists. We're just saying that this web container relates to this database with that name. And once the provisioning happens, this is where the injection happens, but it happens in the distributed fashion. All that wiring happens in the distributed fashion, and the definition, the meta definition, needs to take that into account. It doesn't need to reference to a specific IP, for example. It needs to reference to the logical service behind that. And as I mentioned, a service could be anything, and not necessarily Java. Processes, actually, a lot of that wouldn't be Java. So Java would be just a private case of those services. And this is just a typical example of how an application looks like today. This is a typical big data application. The word typical for big data is not that. Could be an oxymoron for some people, but big data became very common. So this is a true typical environment that I took from one of the architecture. So you could see, for example, Hadoop, Memcache, MySQL, a lot of streaming processing out there. And what you could see is two things. One of them is the heterogeneity, but also the complexity of that thing. What we want in that application context is the ability to describe that thing. Okay, not just one component of that, which is the right layer here or the left layer here, because we have that already. What we want is the ability to define all that. Why do we want the ability to define all that? Because we want to be able to clone that very easily. We want to be able to maintain that very easily. We want to say, take that entire thing, deploy it on Amazon. Take that entire thing, deploy it on Rackspace. If we can define it in a way that can describe all those definitions, then we can actually do that. And if we can't, then we can't. And that's the motivation behind that. So that brings us to the next point. Is that enough? Yes, so one aspect is that we're missing some information. So if we only have the definition of the packaging, meaning what are the tiers of my application, how each individual tier is installed, is that going to be useful enough? So let's say that I'm throwing it out into some orchestration layer, and it takes all that definition and operate around that. Would that be enough? So one point of dimension is that the operation needs to have a lot of information about the dependency. So for example, if I do that manually today, when I deploy a database, it's not just deploying a process of a database, I'm deploying it. Someone needs to know that the database includes my data, that I can actually query the data before I'm launching the web tier. Because if I launch the web tier just when the process of the database is there, it might actually have a timing issue. I may launch the web tier. It will connect to the database, but wouldn't find the data because the data is still being loaded. So how do I know that information? How do I define that type of dependency? If I try to map all those dependencies, I'm going to get to a very chaotic definition or very complex definition. So that part is missing. The other part that is missing is the following thing. And those who have been in these continuous development discussions should be very much aware of that. This is another important aspect of our application, and in cloud, it becomes actually even more important than the packaging side of it. How we operate the application. Ways that information sits today, in many cases, in many places. So you'll find that in scripts, shell scripts, you'll find that in Chef, and some other configuration tools.
So isn't there a bigger question here? It's the dynamic nature of the system?
Right.
Does it scale? Does it talk about how you scale?
Yes, so the idea is that an application also had definition of its operational aspect. So when I want to describe an application, I can't really describe only the component of the application, or even the configuration. I need to describe the operational aspect, the operational dependencies. And operational dependency have aspects on deployment and post-deployment. On deployment, it's pretty much the life cycle, the regular life cycle of installation, configuration, setup, and startup. But the more complex thing is the post-deployment aspect. How do I scale it? What happens when something breaks? What is the failover process? When a tier fails, does that mean what are the dependencies that is going to be broken out? And how do you do that? So you know how to do that manually. There is no reasons why you couldn't really map that to something more automatically. The other thing that we need to know in the post-deployment aspect is also not just how we fail over and scale that application, but also how we maintain it. So for example, when we do an update of a var in a web container, there is usually a process behind it. We do it in a certain order. We do it in a way that wouldn't break the application that is currently running. So there is a lot of that definition as well, a lot of that knowledge as well, that is outside of any description of the application. So if we want to take that application and build it from scratch again, without that knowledge, something is going to break. So this is an application. So what we're basically trying to do is map what is an application as it is done today. And there is all those aspects that we need to take care of. And the reason why we need to take care of that differently than we used to is because cloud, or this type of dynamic world, enforces us to do that. There is almost no way where we could do that effectively without having this knowledge or building the application with that knowledge in place. Now, the other aspect is the consistency. Now, if we talk about heterogeneous world, one of the problems in heterogeneous world, and don't get stuck in that picture, one of the problems is that, think about just having Hadoop and Tomcat, right? How do you install Tomcat? You pretty much know there's a set of things. Try to do the same thing that you do for Tomcat from installation, scaling, and everything to Hadoop, right? It's going to be completely different. Now try to do that to MySQL. That's going to be another thing that is completely different. How do you monitor those things? That's going to be also completely different between all those tiers and application. So if it's not consistent across our stack, the complexity becomes exponential of managing that entire thing. So one of the things that we want to do is make that consistent. Consistent not by replacing the tiers, but by providing a layer that will make it consistent. And that layer is going to map into the individual way of how MySQL do things, but from an operational perspective, it will look the same. So we'll call the same thing. Behind the scenes, it will actually do different things. And in that way, we can actually glue or provide a consistent layer across all those different things. So the way we're going to install Hadoop is going to be very much different to the way we install Tomcat. And that's going to simplify quite a bit the environment itself. So that's the other bit that we need to keep in mind. So we have a very ambitious goal here. Okay? Now the next thing is how the hell do we do that? Okay. One of the answers, and I think those who have been in the Gradle discussion have probably heard that, DSL. DSL stands for domain-specific language. And the idea of domain-specific language is to try to map that problem, which is the domain that we're talking about. The domain is the problem of the orchestration that I described earlier. And now, we want to define something that can describe an application with all those different constraints. So if we take any language today, whether it's Java, Groovy, Ruby, whatever, and try to implement it in those languages, we'll find ourselves doing a lot of verbose things that are not readable because they are not specific to our domain. Again, our domain is orchestration. I don't want to see a lot of code that if I'll walk through that code, I may understand what it actually does. I want to see something that says scale when the Tomcat server has latency of 10 seconds or less than a second with not more than 2 instances. And if it's less than 10 seconds or less than a second, scale it down. That's how I want to describe things. I don't want to describe with a code, with a lot of verbose code that no one is going to be able to maintain or even read. I want to be able to describe that my application has a Tomcat server as a web tier, a MySQL as a database, and they depend on one another. That's how I want to describe things. And I want to have that description in a very non-verbose way to describe it. So a domain-specific language could be a mean to solve that problem. And we'll see how we can use that, and that's kind of a good segue to the rest of the discussion. So a few examples just to give you an idea what is a domain-specific language. You could see that it's not a new concept. We actually implemented that quite a bit even without the definition of a domain-specific language. A good example for that is SQL. SQL is a domain-specific language for managing data. And it's a very successful one. It's actually something that we've had for years. Another example for a domain-specific language is even a regular expression for string manipulation, right? So we've been using that concept for years without necessarily calling it by name. And the idea here is that we could apply that same rule to the problem that I described earlier. And that's going to be the mean to a solution. Now, the other example, and this ties to what you described earlier, doesn't Chef do the same thing? We're actually borrowing another idea of how people have done or solved similar problems. And in the DevOps world, Chef world, Ruby world, there was a concept that was called recipe. So recipe basically tried to not create a DSL that defines everything, but use a DSL that provides a framework in which we could put the definitions, our specific definitions. And our specific definition can be very different. So we're not going to try and create a DSL that has now all the definition that says MySQL has this and this, and the web tier has this and this, because that's going to be an endless work, and it's never going to be doable. Because an application world is a living organism. It's always changing. There is always new application, new features, new versions. There is no way we can map that to one language that could cover it all. So what we can do from a scope perspective is create enough construct in which we could put that specific definitions in a way that is readable. But there's going to be specific definitions per service that is outside of the domain of the domain-specific language, but the domain-specific language is going to give us that framework. For example, how to start the server. The implementation of how to start a server would be different outside of the domain-specific language context. But how we call it and where we call it could be a standard way. And that's the type of trade-offs that we're trying to map here. So we're not trying to create a language that will map the world right now. These are the type of things that we need to have as part of that DSL. What components do we have? What are the dependency between them? How to install the services? Where the application and the binaries sit. So where to grab them from? Is that a web container? Is that a Maven repository? Is that a GitHub? Anything that fits into that. And as I mentioned earlier, the post-deployment aspect. What happens in the case of a failure and so forth, and how to monitor each of those components. So that's the DSL that we want to create. We want to create a DSL that has all those constructs. Okay? Let's go on. Then, by the way, when we have that DSL in place, someone needs to understand it. And this is going to be an orchestration server or something that can read that and execute upon that. So just by creating a DSL, that's not enough. We need an engine that can parse it and understand it and do something meaningful with that. So we need those two components to solve that problem. OK, how Chef does that. This is an example of a DSL in Chef. So what Chef did, and that's an interesting lesson for us as Java users, is took Ruby. So basically said, Ruby has a lot of construct in the language in itself that is a good fit for creating DSL. What are the construct? It reduces a lot of verbose things like columns and semicolons and others, and it can be extendable. I'll show you how you do that in Java, but that was a general concept. And that's what made a lot of the Ruby guys adopting the concept of DSL to do a lot of that orchestration. So what we can see here is something that is more readable. I can actually read that and understand that what we're doing here is basically trying to change a configuration of a web server that is in some cluster. So we're basically doing a search on a cluster, finding the node that fits to a certain name, and setting up the configuration of that. That's basically what we're doing. So again, try to do that in a regular scripting. You'll find that it's much more verbose. So by using a DSL in that context, we could simplify that process because we have a lot of more construct in place and more services in place to help us do that same task. And the result is less verbose, much simpler to read, much simpler to understand. But that doesn't help us. We're here in a Java users group, right? So I'm not going to pitch you Ruby right now, or even JRuby. So the question is, how can we do that in Java? And that's, I think, the answer is pretty obvious, right, from the topic of this discussion. What are we going to use? This is where Groovy fits in. Why Groovy? So Groovy takes a lot of those ideas of those other languages, like Ruby, but do that same thing in Java. The problem with Ruby for Java users is that it's a different domain. Right? Maybe it can utilize the same language or the same JVM, but it's a different language. You can't really use effectively the same modules, the same object. And if you're a Java user, you'll find that context switch is very different. So what Groovy is trying to do is take a lot of those, keep you within that Java domain, but give you a lot of the features of those dynamic languages. So one of the features is reducing the verbosity, what is also referred to as syntactical noise. So for example, if I look at that code, I could see that in Groovy, I can reduce a lot of the things that are not really meaningful to run my application, just by running Groovy without any DSL. Okay, so Ruby in itself gives me power to simplify things just by the fact that I'm using Groovy. So that's the first thing. The second thing is that it's extendable. It's extendable in the case that I can actually configure the compiler and add things into that, like imports. So I can reduce the calls to imports. I can reduce the calls to, for example, I can write something very readable like that. Because it's extendable, move left at 3 kilometers an hour. That's very, very readable. But in order to implement that this line would be actually a code that runs, we need to be able to interact with the actual language engine, the compiler, and other configuration, other things that are called binding in the language itself, meaning the ability to provide context to say, when you run that code, actually run it without import before you actually run that. When you run that code, use that base cloud for every class that you're generating for that particular script. So I can hook and talk to the compiler and do things that will enable me to extend the language. I can even change the class on the fly and say, well, you know what? You could actually add properties into that class dynamically because I know that for that domain, I need those properties in place. And there is a way to control that. So there is a security model in which I can say to the compiler what I'm allowed to do and not allowed to do so that people wouldn't be able to mess up with the DSL and do the wrong things as well. So the basic idea in the language that gives me that power is the ability to interact with the compiler and basically provide that definition on those different points in the compiler that otherwise we wouldn't be able to do. That's what makes Groovy, or Ruby for that case, a tool that is very good for DSL. Another example, and you could see an example of how the code would look like without Ruby and how we could look into the Groovy kind of scenario. It's the command chaining kind of model. So in Java, if we'll try to write something like that, it would look like the things at the top, and we'll need to do a lot of work to actually make that code work, returns and other things. In Groovy, that becomes something that is built into the language itself. So we could call take, which would be a method take, and the second thing that we'll do is we'll pass a parameter. And if we don't pass other parameters, then the second thing would be another method call on that same object. And then another thing is the parameters, but because we're using the second parameters, you could see that we're using this to actually define that these are two parameters for this method. And then if we don't use that, then the second thing becomes another method, and this would be the parameters for that method. But the result of that is very readable. Like as a human, I can read that and understand what it does, even if I'm not a coder. And to implement that, it's much simpler. If I try to implement it in Java, I'll need to actually write that code in that way so that I can do that chaining. So every time that I'm running that class, it needs to return itself in order that the next chain in the command would be able to work on the same instance and so forth, which becomes more verbose for development. So that's another property of the language that makes Groovy more useful for building DSL. So we touched on some of those aspects. Obviously, I didn't cover. There is more aspect to that. But I thought that the main message is that we're using Groovy because it's extendable, because it gives us the ability to control the compiler, and because we can create DSL as a result of that. OK, so now that we talked about the idea, the problem, what we're trying to solve, I wanted to give you an example on how we solved it. And when I'm saying we, I'm the CTO of GigaSpaces. I actually didn't introduce myself. So my name is Nati Shalom, and I'm the CTO and founder of GigaSpaces. And one of the things that we do is we launch a product, an open source project that is called Cloudify. One of the things that we try to do in Cloudify is actually solve a lot of those problems. And what I'm going to do in the next slides is reference to that project and reference to that in a generic way, meaning what are the lessons that we took? What are the methods that we use to address the question that I mentioned earlier? And hopefully you're going to take that as a lessons. And a lot of those ideas, as I mentioned earlier, are generic. So you could very much take it and implement it in your own project. So let's see how we address that. So first of all, when we created the DSL, remember the structure of an application that we look at. So we said, OK, we need to map the domain model of that DSL into that structure. So the constraint or the construct that we have is an application. The core construct is an application and a service. We also have a pod. We didn't implement it yet, that pod model, but that's something that will come down the line. But the main construct are an application and a service. We'll see how that maps into a Groovy-based DSL. So you'll see what I'm talking about. Look at that. Basically, what we have here is a pet cleaning application that, as Java users, you're probably familiar with that. It's a pretty common example that is actually using not MySQL, but using a database that is a Mongo. And Mongo itself is built out of services.
Oh, Mongo daemon model.
Yeah, exactly. So Mongo itself is built out of services, so we describe them as services as well. And that's how we construct that, so we can actually take a complete cluster and map that in that world. And there is dependency between them. So you could see, for example, that the Tomcat service and the Mongo service is dependent on one another. Actually, I omitted the dependency just to make the snippet here something that could fit into that slide. But there is also the dependency, like in this case, on those other tiers that are missed here. So for example, when I'm saying depends on, that means that this one runs after this one.
Like a cluster of Mongo's.
Exactly. So that's an example of how I configure that. But you could see that you could actually read that and understand what that application does and how it is comprised and what are the tiers of that application, how they relate to one another, without understanding very much how each tier works. Now, that's not enough, obviously, but it already simplifies our world quite a bit. Try to go to anywhere in your Java code and find how your application is built in one single file in a very simple, readable way. You'll find PowerPoint presentations that changes all the time and documents and wikis, but never something that is binary, that is baked into your application, and you know that it works. You know that it actually maps directly to the application that is running right now in production, because it's part of the deployment. It's not a definition that sits outside of it, okay? So that in itself is already helpful. Now, you'd ask, okay, that's a good start, but where is the definition? That's too simplistic. Where is the definition of how we actually start that Mongo thing, the Apache thing? There is a lot of details there. How do we use that? And another question that I would add to that is, what if I have already something that defines that? Do I need to build that from scratch now? Forget everything that I've done already? And we'll try to address that, whether I'm using Chef or whether I'm using shell script. Let's see how we're dealing with that. So the second element is a service. The service is the more fat element. This is where we'll have more details. Actually, 90% of the details is baked into that element. What we're seeing is two elements in that DSL of a service, and we'll see more of that. The interesting thing is that it's modular, meaning that a service could be very simplistic. It could include only the metadata of its service and a few other elements, and we can extend those other modules. So we don't necessarily need to have all the components that I'm going to show you right now as part of a service. Why is that important? It's important because when we want to build an application or port an application to that model, we don't know in advance all that information, or we don't have to know in advance all that information. We don't know in advance, for example, how to monitor all the custom metrics and the SLAs that would define the application. And that's fairly advanced in the process in which we're developing that application. And we want to be able to introduce that in stages. We don't necessarily want to have everything pre-baked, because that's going to take much longer process to map the application into that world. So the very basic element is to define the metadata. And the metadata is actually used for the monitoring, less for the actual orchestration. So for example, the fact that we're calling it a database is mostly used by the monitoring side to actually use an icon that looks like a database, so that when we look at the monitoring, we'll know what it is. But we have that definition of a metadata that other services that would be able to query that information would be able to use that for other purposes. So beyond the metadata, and by the way, the other piece of metadata would be other things that we want to add for our properties. For example, what would be the URL for the application? And we can actually add that. It doesn't have to be static. It's something that's computed. I'll show you that in a live application. The other element that is important is the lifecycle. Remember the question that I asked earlier? What if we already have a definition, a script, that we're using right now manually to start and stop my Tomcat server or my Mongo server? Do I need to recreate it? So the answer is generally no. We can only map them into that definition and basically say which script to call in which context. So in this case, we're using a Groovy script as a shell script, but we could also map a shell script here, a .sh, or a batch file in Windows, or have a definition that has, for Windows, run that script, for Linux, run that script. I don't have that in this example, but there is another example of that. Yeah. So there is different ways in which I can set the value for given properties, and that's part of the definition of the DSL, is that I can, and the use of Groovy is that I can put different values easily into the same property. In that case, it could be an array, it could be a string, and based on the value, we know how to act upon that. That's the core part of a service, and by doing that, we can actually map to an application, and we can cover a lot of things. We can cover the consistent deployment. installation, configuration, dependencies, a lot of things just by doing that piece. But we want to do more. Okay, so we'll see how we extend that. What other things we want to do? For example, remember the scaling things that we mentioned? Again, you could read that. Let's see if you understand what I'm trying to do here. Total request, right? Now, try to do that today without a DSL. Have you tried it to do it today? Even go to Amazon and use the watch element and some other services and API that you're using. Try to define the metrics and the rules, and then what to do with that rule. You'll get this size of files. I'm not kidding you. And if you'll understand what it does, beer on me. Anyway, the idea of this is, in my view, a best illustration of the value of DSL. That I could actually condense things that right now fits in a very complex and verbose things and put it in something that is very readable. That's the whole idea. I mean, take everything that I said. Basically, what we want is build readable code that will work. That's, in a nutshell, the only thing that we're trying to do here. All those bits and bytes are the means to an end, but that's really the end goal. So we really want to be able to say, take anyone in our organization and say, tell us what you want to do, write it in a way that you understand it, with all the definition. And now we, as technicians, quote unquote, need to take that definition, that readable definition, and try to make it work. And we'll use the language, we'll use the extendability of the language, and a lot of features that I'm going to talk on, and I'm going to touch on the under the hood things to actually make it codable, to make it something that runs. That's in a nutshell the entire thing. So for example, what we found out is that in order to monitor an application, what we didn't want to do is map replace the entire monitoring aspect. What we wanted to do is monitor only the things that matters, the KPI as they are called, key performance indicators. What we find is that there is a lot of standard. There is JMX in the Java world, there is SNMP, there is tons of things. And if we try to build plugin for everything, that's going to be an endless process as well. And not everyone, for example, Mongo doesn't have any of those standard APIs. They have their own custom API. In some cases, it's a REST API. In some cases, it's just a CLI, a command line interface that you call to actually grab that. In some cases, you actually need to call to log files and grab that information. So in order to make it very simple, what we said is basically per service, all we need to do is have names and values for those key performance indicators. How we grab those values can be different per service. We don't need to know the details of that. That details can be in a closure. That details can be somewhere else. And you could actually call a code, and we don't really care. So in this case, what I'm using is a JMX, for example, but I can map that in the case of Mongo to something else. The result would be that every service returns an array or map object of keys and values that is continuously being updated. So every time that I'm monitoring that service, I'm getting a list with the updated values per key. And then I can apply rules like that scaling rules. So if I have a composite metric, I can map that in that closure. And I can write any piece of code here that says the metrics that I want to scale for is going to be computed metric. What is the logic of that compute is not something that I need to map in the DSL. I'm actually giving the power of the language to do that logic. I'll give you the tools and libraries to do statistical computations very easily, but I'm not going to get into that layer and try to map the world here again. Okay, so the idea is that you could put a closure here and write anything that you want in terms of the logic of that metric. Okay, let's go ahead, another example. So at the end of the day, this is how it's going to look like. So for example, when I'm taking those key values, what you could see here is that I can say this value needs to be monitored as a gauge and another graph and some other things. But the important thing, again, think about how applications are built today, is when I describe the application, I'm also describing the operational aspect of that application, meaning how to monitor it, because I need that information not just for monitoring aspect, I need that information to keep the SLA of the application. What is the SLA application is part of the definition of the application. The SLA could be a latency, the SLA could be availability SLA, and some other things. But once I map that, I can actually have that information baked into that same definition. Okay, let's go on. The other thing that I want to do is say that this script, that definition of application, needs to run anywhere. By anywhere, I mean bare metal machine. I mean Amazon, Rackspace, OpenStack, CloudStack, everything. I don't want that script to be different per environment. Because once I do that, I'm breaking the entire definition. So how do I do that? Because each environment has its own API. Amazon has its own API, its own image format, its own whatever. There's no way that I can find a least common denominator for everything. So what we did is we created something that is called a template. A template basically says, this application needs to run on this type of machine, small Linux. The definition of that machine is going to be different per Amazon, per Rackspace, per whatever, but we'll keep that outside of that recipe, somewhere else, in a place where we call it a cloud driver, where we keep everything that is platform or environment specific outside of the recipe, and that's how we can keep our recipe portable. And all those custom definition outside of that. So we don't necessarily trying to create a least common denominator for everything, but we're trying to minimize that change and the areas of change. Instead of having them scattered around our recipes and code per deployment, they're all centralized in one component. In that case, the portability becomes much simpler. And there's different implementation for a lot of that. So we have a good starting point that in most cases, we don't need to even mess with that. So if we still in that standard world, we'll probably find that the default plugins fit that. And you can see the difference mapping for each of that environment. One of them is in Rackspace, one of them is in Amazon. Each one of them is different, but there is a lot of similarities also between them. I believe that over time, the differences would also get lower. And the last bit is, as I mentioned earlier, what we don't want to do is reinvent the world. As we pointed out, there is already technologies, not necessarily in Java, that is doing a lot of that mapping, the definition of how we install an application. So I mentioned shell script and the ability to call shell script, but there's also places in which we're already using Chef or Puppet or some other configuration management tools to implement a lot of that logic of how we install or run an application. And what we wanted to do is not replace that, even though technically we could, but map to that. And what we did here in the DSL is we enabled to extend a service definition to say how you run the application, how you start it, how you configure it, is defined in a Chef script. How do we do that? We basically extend that, as you could see here, into a Chef. So by extending a service to a Chef, we inherit some Chef properties into that service. What are those Chef properties? Usually, it means that I can actually tell, in this case, Cloudify, what are the cookbooks, what are the recipes that will be called per installation. And in that case, I could inherit or import the Chef cookbooks as part of my service definition and use the service definition to wrap that with extra information that is not part of that cookbook, in most cases, like the metrics that I mentioned and some other properties that are not part of the Chef recipe. So a lot of the installation configuration, et cetera, is something that I can actually import and use and reuse, not necessarily implement. We're doing the same thing for Puppet as well. So the idea is that it would be extendable such that I can plug in those different technologies into that and not necessarily come yet with another configuration management that requires a rewrite of the entire thing. So that's an example of how DSL look like. And that's what we've built to address a lot of those questions. So hopefully that gives you an idea when I'm talking about the DSL as a solution to the problem that I mentioned at the beginning. This is what I meant. Okay, so hopefully that gives you an idea. And again, try to take that in a generic way so you could implement the same thing in your own environment. You don't necessarily need to use that tool. Now, the last part of this discussion, I want to go a little bit under the hood and show how we implemented that DSL. What are the features of Groovy that we used to implement some of those constructs? And I'm going to go through a few examples. I'm not going to cover everything. So let's take the service component that I mentioned earlier as an interesting case. This would be, for example, how it would look like if you would write it in Java. Obviously, I missed a lot of details below, but for the sake of illustration, that should be good enough. What we wanted to do is get rid of the imports and this, a lot of the dots that you could see here, and make it more readable, like the one that you've seen at the beginning, okay? So we're going to use certain features of the Groovy language to get rid of that noise, to make it more readable. Let's see which features we used, and hopefully that will give you an idea. So the first thing that we did is we used constructor with name parameters. So with constructor with name parameters, we can actually pass in a lot of the properties and value without doing all this dot, dot, dot thing. And that in Groovy is built in. And that gives us a way to already omit some of those noise. That's the first feature that we're using out of the Groovy language. The second thing that we're doing is we're interacting. We want to get rid of the import closure, right? The first import lines. How do we do that in Groovy? In Groovy, there is something that is called compiler configuration. The compiler configuration is a component in Groovy that I can actually tell the compiler which libraries or which components to import before it actually compiles my script. And I can tell it what are the libraries that I wanted to import before that. So in that case, the areas, meaning that our code that would run your script, would be able to run it, but before we run it, we do the import outside of your script. And the way we do that is we interact with the Groovy compiler, tell it which classes or which libraries we wanted to import, and only then call your script. And in that case, the compilers already include that definition. It doesn't have to be part of your script. That's the idea here. It's pretty straightforward. Okay? The component, the API that we're using is called the compiler configuration in Groovy. And this is basically how we tell it which libraries, which elements of information we want to have pre-baked before we call our script. And that means that we can omit that information from our script. So a lot of the things that are generic to our script, that are repeatable, is something that we want to take away so that the user wouldn't need to know about that and use. That's how we get rid of the import. So we got to that point where we can have that service definition without the import, without a lot of the noise. So we're already in a good place, but not enough. The other thing that we want to do is extend further. Another feature that we use is that we could tell Groovy, again through that same binding and configuration, we can tell Groovy which base class it's going to use, it's going to generate for our script. Usually what it does by default is using some sort of a default script class as a base class. What I can tell the compiler is that when it's generating my script, it's going to use my classes, which means that I can actually add properties and any methods in that base class that by definition is going to be part of every script. So when I'm writing the script, I can assume that those methods exist without actually writing them or importing them or whatever. And that's how I can extend that very easily. So that's another method in which I can remove a lot of that definition from the script, keep the script simple, and put all the repeatable work outside of that script. So that's another way. Sorry. Exactly. So let me show you an example, and I think that will address. So for example, we wanted to say that every print line, every call to print line, would go to a log. So we did an override of the print line method and made it such that every time that you're calling print line in your Groovy script, it would go to a log. That's an example of how you do override, also for the default implementation. Okay, so it's the same Groovy script. Now we're extending its capabilities with other things just by doing that method. So it's another feature of the language that I used to implement that. Again, I'm just trying to walk through, first of all, the DSL, and then how we implemented that and what features of Groovy we used to implement that to give you an idea how you could extend that yourself. There is much more definition on how you do that, so by all means, there is more references than the one that I'm going to refer to, but hopefully you get the idea. The other thing that we can do is extend the class definition itself. There are different ways to do that. There is a method that is called monkey patching, which basically means that I can actually interact with something that is called meta class in Groovy. And by interacting with the meta class, I can extend the class in runtime. I can add properties, methods, and other things into the class itself. The advantage of that method is that if I do a Java P on that class or something like that on the class itself using Groovy, I can actually see that new definition in the class itself. The method that we chose to use is slightly different. It basically says that it uses a hook that basically means that every time that I'm invoking a property or a method that is not part of the class definition, it will call that method, and I can put a logic around that. The advantage of that is to be very generic. I can put one place with all the definitions. So if I have a generic rule that applies no matter which properties I'm using or which method I'm using, that could be an easy way to do that because it applies to all the classes regardless. The disadvantage is that I don't see that in the meta class. So if I'll go to the meta class, I wouldn't see that logic extended into my class. In our case, that was a simpler solution than extending the meta class because the rule that we wanted to is fairly generic. The last point is the binding. So for example, one of the requirements that we have recipes that are pre-baked with a product. For example, a cloud driver would be a good example for that. One of the things that we wanted to do is ship a distribution of our software into a user, which has its own credentials to the cloud and its own properties and whatever. So before that, what happens is that every time that we ship that software and that libraries, you had to go to the configuration and change it and put your variables in those scripts. Obviously, that means that every time that you change versions and other things, that becomes very verbose and very complex. And so what we wanted is the ability to inject a lot of those properties as an overrides. Overrides meaning that I can take the libraries as a backblocks, take it from GitHub, compile it, and build it, and it will have some default implementations. And I can override it from the outside by injecting my properties into that without touching the scripts. The method in which you could do that in Groovy is called bindings. Okay, so in bindings, I can actually tell and set variables and set properties before the compiler runs your code. And that means that when you run your script, those variables will be available for you with the values that you provided from the outside. And that's the idea here. So you could see an example how we did that. For example, we wanted to have a definition of an image and a pre-start message. The way we do that is we call binding in Groovy, pass in the properties files with those variables, and then when we use our script, we can actually use or refer to those variables, even though they're not, the definition of those variables is not part of the script. So you could see, for example, an icon, an image, sorry, that is part of my script right now, as if it was a variable, but nothing in the script defines that. It's actually done outside of my script, using that properties file, right? But I can refer to that as if it was a variable that was defined in my script. And what we used is we use a naming convention to say if that script has a property file under the name of that script, .properties, then we load it in the binding, and then we know that it's available when we write the script. So that was a way to address that problem. Hopefully that makes sense. Does that make sense? Good. OK, so we're close to the end. So the end result is that we create a lot of that generic definition of application for a lot of things that exist out there right now. So we can use that different script that right now exist in GitHubs and a GitHub repository, and that means that if I want to deploy, and that's the advantage of that, if I want to deploy Mongo, if I want to deploy MySQL, Apache Load Balancer, a lot of those common stack, I don't need to go through the process of defining it. I just grab it and use it. And if I even want to build my own application, in most cases, the areas in which I need to define all those DSLs is only in areas that are special. So for example, the things that we added to the DSL is something that is called extend, like in the Java language, which means that I have a golden image of how Tomcat is being defined generically, but let's say that I want to override the XMX or some other variables of that. I can only override that and still extend that gold image or gold definition without overriding it and then creating a fork. Creating a fork means that if, in the GitHub, someone updated, added more logic, added more metrics, I can really inherit it when I'm doing a fork. So I don't want to do that. I just want to do an override. And that's how we did that. And that's why we can come up with that set of recipes. And because we extended Chef and Puppet, we could also have a lot of those recipes in place that already gives us the power to grab a lot of that information without doing the actual work ourselves. So even though we have a recipe, even though we have all those definitions, we don't want to do that ourselves. So with that, I'll jump to a short demo that will give you an idea how that looks like in real life. Very, very short demo. Okay, and the purpose of this demo is really to map a lot of those abstract concepts into something real. So in this case, I took an example, which is the pet clinic, or the travel application, the Spring travel application, if you're familiar with. And I'm using Cloudify and Chef to deploy it. And we'll see how that looks like and what the end result looks like. The first thing that we're doing in Cloudify is that I download Cloudify on my desktop, and I configured basically the cloud driver for my definition. You could see it somewhere here. Okay, so this is the CLI. So I just started the CLI. The first thing that I did is a command that is called bootstrap cloud OpenStack. And the OpenStack is actually referring to the HP OpenStack implementation somewhere in the network. And what I did by that is created a server that is going to be my gateway to that cloud. So I'm starting fresh. Nothing is installed. There is no Cloudify in that cloud. There is nothing of my environment. The only thing that I did before I ran that is that I set my credentials as part of the driver definition of that OpenStack. I'm not going to go through that right now, but there is a way, take 5 minutes to put all the properties in the right place, and from that point, that's the only thing that you need is to run that thing. The end result of that is that once the bootstrap process is finished, you basically get to that point where you have these things up and running, and if I go to the web console, I can already access that environment. And what you could see is the Cloudify dashboard up and running. And the Cloudify dashboard gives me the information of the application that is running and some statistics. I didn't have to do any of that. That comes out of that, right out of the bat. And the definition includes the application that I deployed, and I'll show you what I did to deploy it. And also the management of Cloudify is also treated as an application. So when we deploy Cloudify, we deploy the REST gateway, and the management console, which is a web server and everything like that, is also treated as an application, so we can monitor that using Cloudify itself. So Cloudify in itself monitor itself. So we can see some aggregated value of the total memory, total CPU, of all the aggregated machines that exist out in the network, and I can see some of the aggregated information about the number of servers, the type of servers, the type of services that are totally running right now. The second thing that I did was to install the application, and I did that using a single command that is called install application. There is two commands. One of them is install application. The other one is install service. Install service would install the individual component, the database, the Mongo, whatever. Install application would go to the application definition and would run the entire thing, all those composite applications, composite services. So in this case, I did an install application, which basically goes to the definition of the application, figure out which elements needs to be running. In this case, it's a MySQL plus WebTier plus load balancer, and it deploys it. And you could see some of the output in the console of what happens to do that. And I can actually, at the end of the day, see the result of that here. So if I go to the application, I can see the topology of the application that is actually taken from the definition of the application DSL. I can see the dependency of each one of them. I can see that there are currently 2 instances of Tomcat running right now. I can see if I click on one of them, I can see different views of that Tomcat. For example, I can see the custom metrics that are part of the DSL. I can actually see that one of the servers takes more load than the other. All that comes out of that. I didn't have to do any of that to actually get that monitoring. Once I deploy the application, because the application includes that metrics, I can create that view dynamically. Because there is a definition already that the monitors understand, which is the DSL, I didn't have to go to the monitoring and say, my application is built out of those things and those things and those things. It actually understands it, parse it, and create that view automatically. That's the beauty of that. Now, the other thing that I can see is this thing. And this one is red, for example, right now. Why is that red? One of the common problems on managing clusters is managing or understanding how the cluster is balanced. Everyone that runs clusters at some point find out that one customer is taking more load than the other. Twitter, for example, is a very good case for it. And usually a lot of the crashes that we have is because of that, because one of the nodes, we didn't partition well the cluster, one of the nodes takes most of the load, it explodes, it breaks, and then the entire cluster gets down. So we wanted to have a very simple view in which we can know how our cluster is doing So the gouge here shows us the aggregated result of those individual servers. Remember, we have a cluster. Each cluster has a different value for that same metric that we're monitoring. We could have, all those metrics exposed to that, which is going to be very verbose. A lot of information that we don't necessarily can pass, or any human being can pass easily. Only thing that is matters for us is if something is wrong. That's it. If something is not wrong, we don't really care about those different metrics. So we want to have and pass that information very quickly so that you know if something is wrong or not, and that's it. That's what we did here. So with that gouge, we know if the cluster is balanced without drilling into the details, and then once it's not balanced, then we'll drill down into the details, but only then. And we can see the logs and some other information about the instances that is running, and we can go and see the details, the meta information per service. For example, in this case, I can say, go to and see how the load balances in the cluster. And it actually sees 2 instances running right now. It's actually started with 1, and I did something. I did a scaling event. I simulated. It just takes, the process takes a little bit of time. I emulated a scaling event that created another instance, and that added automatically to the load balancer. So again, I didn't have to do anything. The only thing that I did here is trigger a scaling event, and that created a new Tomcat server, and that Tomcat server automatically configured that in the load balancer, and everything went up automatically. The same goes with failover. So if I crash one of those instances, what I'll see is that it will monitor the SLA, say that there needs to be 2 instances here, it will launch a new machine, configure that, and that's it. So with that, I think we're reaching to the end. I'll just show you the examples of how I did that trigger of event. So all I did here is set instances up 2. Up is the name of the server. So for example, I did here list services, and I can see the name of the services that are currently being deployed. And then I can interact with that. Take into account that I didn't have to point any IP address, any host, or anything like that. I interact with the service using a logical name. Because of that, I can take that same application and run it on a bare metal environment, on a cloud environment, or any environment, and it will work. Because we abstracted a lot of the infrastructure details out of that recipe.